And then there's
I forgot to stop the recording.
yeah, okay. And then there is one important feature that everything relies on, and I think people had trouble stating it correctly. So every the A of it should be a subset of reals, but there's you might consider any Polish space. Okay, times ordinations in W. Whenever you have a set of real set of R plus ordinals in W, it has an internal definition. There is there are phi Z in R and B in G such that A is equal to the set A is equal to the set of all reals such that VRZ satisfies phi R. Okay, so I want everyone to stare at this for a moment because it's a concept that is that occurs in Wooden's work and in work on models of determinacy, but here we have some sort of variation. Right? So whenever you have a I should say in R plus ordinals, say that so whenever you have a set which consists of pairs, reals and ordinals, then it has an internal definition. What does it mean? What is an internal definition? It's a formula, a parameter, real parameter, and then some parameter B, such that the set A consists of those pairs R alpha, such that the model which contains this this little parameter and that R we are talking about in the first place satisfy that.
It's a Soloway set or something like this.
Yeah. That's what it is. Okay, say that there are many I don't think this is a complete axiomatization. But certainly there are people are using tricks that can escape this axiomatization. But in fact, I think every substantial theorem can be proved about the Soloway model can be proved from this. Okay. So as we will call this is the internal definition. By the word internal, I mean that this satisfaction relation pertains to the model BRZ. So we do not have to actually reach out to W check what whether it is satisfied. Okay. All right, so what I want to do as a first small exercise is to show that from this axiomatization it follows that every set of okay, so that's one. Couple of observations. Omega 1 of W is an inaccessible cardinal in fact, a strong inaccessible cardinal. Why is that? Well, because if it was, let's say, a successor, let's say if it was a successor cardinal, okay, then the predecessor would be countable in W. That would be a real that there would be a real that is that calls ordering of that order type of the predecessor cardinal, and in V of R of V of that real, omega 1 would be unactual. Omega 1 of W would be actual omega 1 of VR, but VR satisfies the axiom of choice, so it would see a sequence of distinct reals of length omega 1. Okay, and we know that this doesn't happen. Then you have to rule out that it's a singular cardinal. You have to rule out that. So you have to do strong part. That's basically the same. Okay? And another observation I wanted to share with you. So if and this is also true for any other at the same reason. And one thing that I would like to share with you also is this, that if let's say K is the filter generated over VR by a poset which is countable in W, then it's still true that every real of W is generated over VRK by a poset which is countable. Every real. W is no, by poset by counting. When I say countable, I mean countable in W. Okay, and this is simply, I mean, well, the point here is that this model doesn't have to be generated by a single real over V, but it still has this property that every real is generated by countable poset because that's some sort of factorization. Okay, so these are two observations. Out, and then it's a simple. Now it's a simple theorem. Deal. Now observation. So what do you do? So let. Let A be a flexibility. And then it has an internal definition. Find definition five. And in the model, look at V is the real number. And now this VZ, consider the random algebra in right? Well, consider that it's a complete, it's the world sets modulo the null sets, it's a complete algebra, it's a complete Boolean algebra. Find the Boolean value. B and P. The Boolean value of the statement the okay, so but statement of the forcing language, in fact, here you can omit this because the generic, this is exactly the generic extension. This is the generic. Okay, just ask whether phi is going to hold in this model, but this one actually generic. Okay, and then so then because the random algebra is a complete Boolean algebra statement has Boolean value. It's a problem. Now let be the equal to D and all null sets. Let me do set. Maybe delta with null sets coded in BC. Now because BC, we see that omega 1 is strongly in excess of a cardinal, so it has only countably many. I mean, from the point of view of W, it has only countably many null sets in it. So this union is null. Okay, and then we just argue that A delta B is a subset. Okay. But whenever you have a real which is not in D, it's a random real over BZ. Okay, and then so by the forcing theorem, this is going to the random real is going to satisfy the internal definition, just in case it is in this Boolean value, an element of this Boolean value. Okay. So All right, so this is just a very brief introduction to the solving model. Of course, I'm not saying anything new. I wanted to give you this axiomatization. I'm going to use it over and over, I'm sure you will find it easy. All right, so now, so what happens in geometric set theory is that the models that are obtained, they are all models of they're all models of ZF, which are generic extensions of the solving. Okay? And they're generic extensions by simply definable forcing, just certain properties, so-called balanced forcing. Okay. Balanced forcing is something like proper forcing for choiceless. Okay, it's very, very flexible, and you can design many balanced forcings to give you very specific statements. Okay. Of course, it has certain limitations and so on. Anyway, what I will do today, I will tell you what balanced forcing is, and then I will give you the first couple of examples and the first theorem. Okay, so let me just say the balanced forcings, they're going to be definable, and their properties are typically going to be analyzed in the models of axiom of choice of this type. Okay, not really in W. In the end, of course, what we get is we look at the generic filter over W and form that generic extension, and that will be. But plenty of the analysis will be performed in the in models of axiom of choice, intermediate models of this type. So the definition that I'm going to state accordingly is a definition in ZFC, not in ZF. Okay, if you wanted to say it in ZF, actually you would get a quite different. So definition a hypothesis. We balance. Now, first of all, it has to be easily definable. There is no such a thing as undefinable balanced force. That doesn't make sense. So, is this means that there is an ambient Polish space. Okay, like this, P is a vector X. It's an analytic set, and that's an equal its relation P is such that when you start thinking about this complexity requirement, it becomes clear that what you really need to assume, I'm never going to bother with this. What is forcing? Okay, people tell you that's a partial ordering. Okay, but in fact, you don't really need that. You just need this relation to be transitive and to contain the identity. You don't ever care about the anti-symmetry. Okay, it's completely irrelevant. And but when you actually, that sounds like nitpicking, but in fact there are many concepts I will never really stop to actually confirm this complexity calculation. But if you do it, then sometimes if you want to get a partial ordering as opposed to just a transitive relation, you realize that you would have to approach it out by some equivalent installation, and all of a sudden it would fall apart. Okay, and but this point is again, it's just when you look at what people mean when they talk about forcing, they all say this is a partial ordering, but they don't mean that. They just mean it's transitive and contains the identity. Okay, just a small point. Here, in fact, it becomes somewhat okay. Here's another thing, and then there's the second requirement. There is a cardinal law. It can be pretty long. Okay, such that whenever P is P and VG0 VG1 are mutually generated. Extensions of the model that we are working in, and both of them collapsing lambda to omega. And B0, then there are P0 there are P0 in VG0 and P1 in VG1, which are both stronger than P. Such that for every Q0 less or equal to P0 and Q1 less or equal to P1, and these two belonging to their corresponding models, Q0 and Q1 are. And the formula is super helpful, but when I draw the picture, it will become clear. And after a couple of maybe observations, it will become a very natural motion. So, picture. So here is our model V, okay? Model of CFC that contains the definition of P as follows. Now, there is some condition in it. Okay? Now, there will be a lambda which commonly is just a continuum of P, but it could be something bigger than that. Say that whenever you take two mutually generic extensions, which collapse this lambda to 0, then there will be some strengthenings, P0 in this one and P1 in this one. So that whenever you strengthen this one in arbitrary way within this model, and this one within this model, then there will be an amalgamation, right? So all right, so I have to give you a couple of examples of this when it actually occurs, when it fails. And at this point, I would just like to say, it's useful to view it as some sort of amalgamation property of the partial order. Yeah. In fact, it has many correlations with amalgamation properties as they are studied in model theory. Okay? And notice that how important it is to assume that the partial order is unknown. Because in order to make sense out of this whole diagram, you have to be able to reinterpret the partial order in this model and in this model, because you see, you're talking about a condition in P which is in VG0. Okay, what I mean is in the interpretation of P. And where is this upper bound going to be? It's going to be in the interpretation of P in VG0 G1. Okay. So if you didn't have this first line, the second line would not make any sense. Okay. So now a couple of examples of what is balance and what's not. Okay. So there's a flat book written on this, and I'm still producing stuff. So I mean, there are very many balanced both sets. It's somewhat like proper forcing. It's very flexible. You can prove. There are many tasks that you can perform with balanced both sets after some. So these examples that I'm going to give you, they're just very, very initial ones. Examples. So I suppose the simplest example at all is just that the previous countable functions, partial functions. Order. So basically what you're doing, you're adding a subset of reals by countable conditions, right? You have a countable piece of characteristic function in the future set, ordered by extension. That's so why is it at all balanced? Right? So what's this? So let P be in any condition, okay? Extended to a total function. I will call this P bar. A total function from R to 2. This is not a condition in P because it's not countable. Okay. But if you look at generic extensions, which collapse the cardinality of ground model V to countable, it will become an element of P. Okay. So in such generic extensions, let this be P0 and let this be 1. Okay. Now, if you extend it P0 and you extend it to P1, these two functions must be compatible. Why is that? The only the only thing that you need to show is that Q0 union Q1 is a function. Must not disagree on an element of common domain.
So the bigger function is smaller, right?
Yeah. So what you need to show is that Q0 union Q1 is a. But this obviously is the case because what is the intersection of the domains? The domain of this function is a subset of VG0, or the domain of this function is a subset of VG1. VG0 intersection VG1 is P because these are mutually generic extensions. And so, so the intersection of the domains Q0 and Q1 is a subset. But we in fact initially took care to define all values in V. Okay, so that's why I took this P bar. This was a function. This was a total function. I didn't leave any spaces open. So I didn't leave any option for these two. Non-example. A non-example would be P countable linear orders on R. Ordered by an extension. Why is this not? So what you're doing, you're attempting to generically produce a linear ordering on the rails, which has countable initial segments. All initial segments are countable. That's what you're attempting to produce. Can't be balanced because and sub P, no matter what the P0 you choose here, P1 you choose here, you can certainly strengthen P0 and P1 so that in its domain, you have some element of VG0 which is not. Okay? So as soon as you added a real. Okay, so extended P0 by Q1, so that Q0 contains in its domain some element of VG0 set minus P. And this one contains some element of VG1 set minus P. Okay. So how would you want to find a common on the bound? That will be very hard because these two elements, let me call them R0 and R1. And maybe X0. X0 and X1 in the common lower bound, they would have to be ordered in some way. Either X0 is less or equal to X1, or X1 is less or equal to X0. Let's say X0 is less or equal to X1. Oh, that is a problem because the initial segment of the below x1 in the condition q1 didn't contain any elements of VG0 set minus V. Okay, it just contained elements of VG1. So you place x0 below some element of this partial orders, which means that you're not ending set. So this is not. Okay, and let me show you one more example. These are just initial examples, and P is equal to part of the omega module of finite. Okay, so infinite sets. By so why is this balanced? There's a small observation. Suppose that U is a contractor. And suppose that an unprincipled object. Suppose that VG0 and VG1 usually generate. And they both contain some sets which modulo finite diagonalize U. Okay. Containing Q0 and Q1 diagonalizing it. Then Q0 intersection Q1 is in.
I'm sorry, diagonalizing?
Yeah, diagonalizing means that it's a set such that for every set in the ground model in the ultrafilter U contains all but finitely many elements of Q0 or Q1.
So it's like in Matthias forcing, we have this
Yeah, that's
function below that.
Q0 intersection Q1. Well, why is this true? Because, this is mutual generosity. Why is was the I suppose you need to just go into the forcing relation probably. So there would be a partial order, let's say Q0 and Q1 to generate. Actually, there would be names for these things. For elements of Q0. Then you would realize that the set of below every condition in Q0 and below every condition in Q1, the set of possible values is still in the ultrafilter. Cannot be disjoint. And a different way of looking at it is to prove a theorem that if you have two disjoint sets in, disjoint sets of ordinals in mutually generic extensions, they can be separated by, disjoint sets in the ground model. Okay, and then, but if you have two disjoint sets in the ground model, only one, at most one of them can be. Okay, so how do you, how do you, actually, prove that this is, how do you prove that this is? What I do is, as an infinite B is right? I will find a non-principal ultrafilter. It's a non-principal ultrafilter. And then I will find a function P0 here, which diagonalizes the ultrafilter and is Zapletal. So, and here I will find one, and this diagonalizes. Hey, you take any Q0 below it, it still diagonalizes the ultrafilter. Subset. Here, still diagonalizes. Yes. So, what you can do then first is, it's one more partial order. It gives you a Ramsey ultra. Okay. Doesn't matter. Reals, is your answer. Now, what I would like to do in the rest of time, I would like to show you that first, there are many preservation theorems for balanced forcings, such as there are many preservation theorems for proper forcing. And one of them, one of the theorems that is kind of curious is theorem in all balanced extensions of the following model, there is no maximum almost disjoint family sets of non-trivial. So this is somewhat curious because the non-existence of mad family even in the solving model, this was open for a long time. But in fact, there's a simple proof which actually works even for balanced extensions, not just for solving model itself, but for balanced extensions. When I say balanced extension, I mean the both sets that we are dealing with, they need to be balanced in the intermediate models of CFC. They will not be balanced in W itself, okay? But they need to be balanced in the intermediate models. Okay. Proof. But P balance. Let P and P forces. Okay. Third information in W. Okay, we have a name for it. Well, tau is really a set of reals. Okay. It's the set of all pairs Q QX such that Q is in P, X is a subset of natural numbers, and Q forces, it's intolerable. So find a, by axiomatization, find an internal definition. For then, so five. Now, let's, I wanted to do something else. Okay, so, I think I'm way too. So anyway, this is one of the theorems that okay. Yeah, good.